Hey, what up? It's your boy Jolly. I'm here to talk to you guys about some kind of pre-trigonometric stuff. I kind of struggled with what to call today's lesson, but I'm just going to call it angle stuff. First up, I apologize for my handwriting on the iPad. It's not as pretty as my board handwriting, but I'm getting better. You guys, before we get into standard position, which is a big part of this lesson, I first want to remind everybody about special right triangles. Now, I know you can have special right triangles of any size, but from here on out, I really need you guys to think about special right triangles with a hypotenuse of 1. Now, if you have a 45, 45, 90 with a hypotenuse of 1, you can do a little Pythagorean theorem and stuff, which I think I linked in my last lesson. But this side is going to be root 2 over 2. You can use Pythagorean theorem to figure that out. But from here on out, if you don't have that kind of on lock, like memorized, you need to know 45, 45, 90 with a hypotenuse of 1 has 2 matching sides that are root 2 over 2. Similarly, if I draw a 30, 60, 90, where this small side is 30, this is 60, and the hypotenuse is 1, the side directly across, let's do a different color, across from the 30 is going to be 1/2, and the side directly across from the 60 is going to be root 3 over 2. I think that comes up in your warm-ups on your assignment today, so yeah. Dedicate those to memory. If you don't have them on lock, put them on a flashcard, memorize them. I'm not a big fan of memorization when it comes to math, but TBH, I do have those completely memorized at this point. So we are going to use those eventually, but right now let's talk about standard position. So you might see some problems where they tell you to graph an angle in standard position. What that means is if you start with the X and Y axis, got the X, got the Y. If you are going to graph something in standard position, it always starts on the X axis. So let's say we put a little arrow here, and then it rotates counterclockwise. Realize this is counterintuitive because you'd think positive angles would rotate clockwise, but they don't. Positive angles rotate counterclockwise, and negative angles rotate clockwise. So if you were to ask, somebody asked you to graph a 45-degree angle in standard position, you do your best estimation of a 45-degree angle right here, and it starts on the positive x-axis and then opens up this way, counterclockwise. 45-degree angle. So that's a 45-degree angle in standard position. Just another example. Let's say somebody said graph, let me think, 200 degrees in standard position. Once again, you would start with your X and Y axis. So here's your X, here's your Y. And then let's go blue this time. It would start on the X axis. They always start on the X, positive X axis, and then they rotate counterclockwise from there. So 200 degrees. Let's keep track with me. Here we go, 45, 90, 135, 180, so a little bit past 180, like right around here is where 200 would be. So this would be that angle graphed in standard position where this whole thing opened up 200 degrees. That's a degree mark. Cool. Next thing I want to talk about is something called coterminal angles. Coterminal angles. I'm lazy, so I'm just going to use the little alligator for the angle symbol. Coterminal angles are angles that in standard position terminate in the same place. So, for example, if I have an angle of negative 45 degrees. Let's go green. So negative 45 degrees would rotate clockwise, not anti-clockwise, as the Brits say. Negative 45 degrees would be right here, where this angle, where it opened clockwise, is negative 45 degrees. Now, a common test question is like, find an angle that's coterminal with negative 45 degrees. What you're going to want to do is find the angle, hold on, how thick is that? Yeah, it's good there. That starts on from the positive direction and goes all the way around to the back side. So, if you think about how far that other angle went, from here to here, that's 90 degrees. Then from here to here is 180. Then here to here is 270. And then you have 45 degrees more on 270. So if you take 270 plus 45, what's that? 315, I believe. So the coterminal angle, if you go all the way around the backside, would be 315 degrees, where it starts here and goes all the way to here. Where to be purple on this side, and then purple on this side. So 315 degrees and negative 45 degrees are coterminal. That handwriting is just awful. I apologize, you guys. The last thing I want to talk to you guys about is radians. Now, raise your hand if you've ever heard this in a math classroom before. Oh, look, everybody raised their hand because everybody took AGS 3 or Advanced AGS 3 or some sort of course last year that talked about radians. Okay, keep your hand up if you know exactly what a radian is. Oh, a lot of people put their hands down. Weird. You guys, a lot of people like just think about radians that they're another way to describe a rotation, which is true. That's what it is. But I think people forget where a radian comes from. So just real quick, if I were to take a circle, yeah, let's redo that. You can do better, Joel. Come on. Here we go. Slightly better. Okay. Let's take a circle and then center it. Put the origin, the center on the origin of the XY axis. But this is your x-axis, and this is your y-axis. Now, 1 radian is if you were to take, let me go orange, the radius of this circle. Let's label it lowercase r. Pretend that that's like made of string, and then you were to, take that piece of string and then wrap it starting here around the outside of the circle. So it'd be like right about there, something like that. Trying to be accurate. This, if you were to take that radius and wrap it around the outside of the circle, this is 1 radian. Now, do you guys know how many radians fit into a circle? Some people do, a lot of people don't. Here, I'm going to do my best to kind of estimate it. So if I took that string and kept wrapping it, it would be like another one around here, something like that. And then, that's the cutoff point. And then I'd wrap it again. It'd be like somewhere around here, and then wrap it again. And then here, and then there. And then you'd have this little gap right here where you'd get like part of it. So if you count them up, it's like 1, 2, 3, 4, 5, 6, and some change. Fun fact is it's about 6.28 radians that fit into a circle. Now that might not seem like a number that jumps out in your brain, but if you divide it in half, it's 3.14, which means there are 2 pi radians in a circle. Now, we're gonna work a lot in radians down the road, but for now, I just want to show you guys how to convert between radians and degrees. So if you are gonna go radians to degrees, you take your radian and you multiply by 180 over pi. So radian, and then multiply it by 180 over pi. If you are going to convert from degrees to radians, so the other direction, so degrees to radians, gosh, my handwriting, I'm sorry guys. You would take your degree and then multiply by pi over 180. So you're always multiplying by 180 over pi or pi over 180. The way I remember this is that if you draw a circle, remember that we just talked about how the whole circle is 2 pi radians. So that means if you just chop it in half, that this top half here, which is a full 180 degrees, is the same thing as pi, because there would be 2 pi radians in a full circle. So pi is the same thing as 180 degrees. So if you're dividing, we'll highlight here, 180 degrees divided by pi, they're the same thing. So it's really like you're not changing it. You're allowed to do this because it's kind of like a giant 1 is how I think of it, because 180 degrees is the same thing as pi radians. So if you're multiplying by something over itself, it's just you're multiplying by 1 and you're not cheating. A couple examples. Let's say change 135 degrees into radians. So because that is degrees into radians, I'm going to want to multiply by pi over 180. So we do 135 times pi over 180. Now think of the 135 as just 135 over 1, and then when you multiply these together, you get 135 pi over 180. Now, the 135 over 180 here on top, come on, buddy, or sorry, this part. The 135 divided by 180, that giant fraction can be reduced. So you could do it the old-fashioned way, finding numbers that come out of those, or you could just type 135 divided by 180 on your calculator and then hit math, answer to fraction. If you do not know about the answer to fraction button, you need to seriously start living your math life and discover it. Google it. 135 over 180 is 3 over 4. So this whole thing reduces to 3 pi over 4 radians. Final answer. Next example. Change. I'm just going to make up a radian. 2 pi over 3 into degrees. So back up here, radians into degrees, I need to multiply by 180 over pi. That's usually where people make mistakes with this, is they forget, was it 180 over pi or pi over 180, and they do the wrong one. I always think that if you're trying to change radians into degrees, that degrees usually don't have a pi in them, and radians usually have a pi in them. So if we are going to cancel out that pi to turn it into degrees, then I'm going to need to have the one that has the pi in the denominator. So it's 180 over pi, because then the pi's go away. And then we just get 2 times 180 over 3. 3 goes into 180, 60 times? Then 2 times 60 is 120. So we got 120 degrees here. Final answer. I think that's it for this first worksheet I'm going to throw at you guys. I'm going to upload it in .doc format instead of PDF this time because somebody requested that I do that. It's easier for you guys to work on. Let me know if that is the case. All right. Hope everyone's doing well. Great to see everybody.